College Algebra, Module 9, Topic 9.2, Inverse Functions and Their Representations. Objective 1, Inverse Operations. Just as addition and subtraction are inverse operations, functions can be inverses of each other. Start with the number x. Adding 3 and then subtracting 3 will give you x again. Therefore, adding 3 and subtracting 3 are inverse operations. Start with the function f of x equals x plus 3. The function g of x equals x minus 3 is the inverse function. These functions undo each other. Let's do some examples. Describe verbally the inverse of each situation. Well, if you open a car door, get in, and start the engine, what would the inverse operation be? Well, it would be you turn off the engine, get out, and shut the car door. You basically undo each of the operations in the opposite order. If the situation is divide a number by 3, then the inverse would be multiply a number by 3. And if the situation is multiply a number by 5 and then add 4, the inverse operation would be subtract 4 and then divide by 5. Objective 2, one-to-one functions. A function f is a one-to-one function if, for elements a and b from the domain of f, a does not equal b implies f of a does not equal f of b. That is, different inputs always result in different outputs. If you'll remember, a function is a rule so that every x value has one and only one y value. A one-to-one function means every y value also has one and only one x value. For example, determine whether the function is one-to-one. Well, we could go through and pick some points. If x is 0, f of 0 would be positive 12. If x is 2, we would get negative 4 times 2, which is negative 8. Negative 8 plus 12 would be 4. If we picked x as 5, we would get negative 4 times 5 plus 12 would give us negative 20 plus 12, which is negative 8. Do you see that anytime we pick an x value, we're going to get a different y value? Therefore, this function is one-to-one. Now the second example, f of x equals the square root of 25 minus x squared, we could also go through and plug some points. If we picked x as 0, then we get the square root of 25 minus 0 squared, which would be the square root of 25, which is 5. If we pick 2, then we would get the square root of 25 minus 2 squared, which would be the square root of 21. If we picked negative 2, though, we would get the square root of 25 minus negative 2 squared, which would be the square root of 25 minus 4, which again would give us the square root of 21. Notice we picked two different x values, but we got the same y value. Therefore, this function is not one-to-one. The vertical line test. This is the test that says if every vertical line intersects the graph of a function at no more than one point, then the graph represents a function. For example, use the vertical line test to determine whether the graphs are graphs of functions. Well, for this first graph, pick a vertical line. Notice we touch the graph in one place. Pick another vertical line. We touch the graph in one place. We could do this throughout the picture, and we're only going to touch the graph in one place. If you can do this and hit the graph at no more than one point, then the graph represents a function. Look at graph number 2. Same thing. We could run a vertical line across the graph from left to right. We are only going to touch the function in one place. Therefore, yes, this is a function. Objective 3 is the horizontal line test. This says if every horizontal line intersects the graph of a function at no more than one point, then the function is one-to-one. So our first example says use the horizontal line test to determine whether the graphs are graphs of one-to-one functions. Well, notice as soon as we pick a horizontal line and it cuts that graph in 1, 2, 3 places, as soon as that happens, that means that your graph is not one-to-one. Remember, it was a function on the earlier slide, but it's not a one-to-one function. The second graph, however, if you start your lines one place, you intersect in one place, intersects in one place. So this graph is a graph of a one-to-one function. Here's something to think about. Is a constant linear function always one-to-one? Well, remember, a constant function is a function that's a horizontal because the y value never changes. Yes, it is a function because it passes the vertical line test, but as soon as you start the horizontal line test, notice the y values are all the same. So a constant linear function is never a one-to-one function. Something to think about, number 2. Is a non-constant linear function always one-to-one? Well, if it's non-constant, that means there is a slope, so it's either rising constantly to the right or falling to the left. Well, because the vertical line test passes, and then the horizontal line test passes because you're only going to hit it in one place, then a non-constant linear function is always one-to-one. Number 3, is an odd degree polynomial function always one-to-one? Well, if you'll remember, the graph of y equals x to the third looks like this right here. It passes the vertical line test because it is a function. It's going to pass the horizontal line test, so it appears that it would be one-to-one. But remember, you can have a third degree polynomial function that looks like this. There can be at most 2 turning points. Therefore, there is probably going to be somewhere in that graph that you're going to intersect the graph in more than one place. So an odd degree polynomial function is not always one-to-one. Sometimes it is, but not all the time. And then the last one says, is an even degree polynomial function ever one-to-one? Well, remember the ending behavior on an even degree polynomial. Either both ends go up or both ends go down. Therefore, it's always going to fail the horizontal line test. So an even degree polynomial function will never be one-to-one. Okay, as a note, a function that is increasing or decreasing on its entire domain must be one-to-one. If there is at least one turning point, then it is not one-to-one. Okay, objective 4. Inverse functions. Let f be a one-to-one function, then g is the inverse of f, and f is the inverse of g if f of g of x is equal to x for every x in the domain of g, and g of f of x is equal to x for every x in the domain of f. Later on, we're going to ask you to show that f and g are inverses of each other. The way you show that is by doing f of g and g of f and showing that you get x for both of those. Now, notation for the inverse function is denoted by f to the negative 1 power, and we read that as f inverse. Okay, if we go back to our pictures, this first picture represents the domain of f. So this is the set of all x values that are in the domain of f. Well, when you apply f to those domains, that gives you y, which is the range of f. Well, the way inverse functions work is the range of f becomes the domain of f inverse. So if you take the domain of f inverse, which was the second set, and you plug it back into your f inverse, then what you're going to get is the range of f inverse, which was the same thing as your domain of f. Okay, objective 5, showing that functions are inverse functions. Like I said earlier, to show that two functions are inverse functions of each other, you must show that f of g of x is equal to g of f of x. Okay, let's do an example. Show that f of x equals x to the third minus 1, and g of x is the third root of x plus 1 are inverses of each other. Well, to do this, we have to show that f of g of x is equal to g of f of x. Well, remember, f of g means we start with our f function, which is x to the third minus 1. And we're going to go in, and everywhere we had an x, we're going to substitute g of x. So that means the f function is going to be the third root of x plus 1 to the third minus 1. Well, the third root of x plus 1 to the third power is just x plus 1. Then to finish it out, we have minus 1. Well, f plus 1 minus 1 would give us just x. So f of g of x is equal to x, halfway there. The second time, we are going to do g of f of x. Well, that means we're going to start with our g function, which is the third root of x plus 1. We're going to go in, everywhere we had an x, we're going to substitute in x to the third minus 1. So what we've got is the third root of x to the third minus 1 plus 1. Well, under the third root sign, we have x to the third minus 1 plus 1, which is just x to the third. Well, the third root of x to the third is just x. So we have shown that g of f of x is x. Because this holds true for both cases, we know that yes, these two functions are inverses of each other. Let's do some more examples. Determine whether each function is one-to-one, and if so, find its inverse. Well, the first function f is 1, 2, 2, 3, 5, 8, and 3, 5. So the way we tell if it's one-to-one is if all the x values are different, which they are, then all the y values have to be different. We could also graph this if we wanted to. The ordered pair 1, 2 is over 1 up 2. The ordered pair 2, 3 is over 2 up 3. Over 5 up 8 up here, and over 3 up 5 is right here. Notice this does pass the vertical line test. and it does pass the horizontal line test, so we would say that yes, this is a one-to-one function. To find its inverse, basically we're just going to switch our x's and our y's. So f of negative 1 would look like 2, 1, 3, 2, 8, 5, and 5, 3. Because remember, the domain of f becomes the range of f inverse. And the range of f becomes the domain of f inverse. Okay, let's do example 2. Is this one one-to-one? Well, the x values are all different, so we're good there. But notice we've got an x value of 3, which gave us a y value of 7, and we've got a different x value of 6, which gave us a y value of 7. Because we had two different x values that gave us the same y value, that means this function is not one-to-one. Objective 6. Finding the equation for the inverse. Let's say they gave us the equation y equals some function. The first thing we're going to do is replace f of x with y if necessary. The second thing we're going to do is interchange x and y. Then we're going to solve for y equals and replace the y with f inverse. Note that any restrictions on x and y should be considered. Let's do some examples. Find the inverse, if it exists, of f of x equals 3x minus 5. Well, because they gave us f of x, we're going to say y equals 3x minus 5. Second step says switch x and y, so we're going to get x equals 3y minus 5. Now we want to solve for y equals, which means we're going to get y on the side by itself, so the first thing we're going to do is add 5 to both sides. So we get x plus 5 equals 3y. Then we're going to divide both sides by 3, so we get y equals x plus 5 over 3. We can go back to how we started this topic in words to find the opposite of 3x minus 5. Instead of subtracting 5 and then multiplying by 3, to find the inverse, we're going to add 5 and then divide by 3. So our last step says replace y with f inverse, so f inverse is going to be x plus 5 over 3. Then it says to give the domain and range of f and f inverse. Well, the domain of f, notice that f has no fractions and no square roots, so the domain would be all real numbers. Because we can get positive numbers, negative numbers, and 0 once we plug in values of x, the range of f was also all real numbers. When we look at f inverse, we have a fraction, but notice there's nowhere for the denominator to be 0, so the domain of f inverse was all real numbers. And the range of f inverse, because we can get all different possibilities there as well, is also going to be all real numbers. So like we said earlier, the domain of f is going to be the same as the range of f inverse. And the range of f is going to be the same as the domain of f inverse. Let's do another one. Find the inverse, if it exists, of f of x equals 4x plus 6 over 5. Well, we start out by replacing f inverse with y equals, so we get 4x plus 6 over 5. Then we're going to switch x and y, so we get x equals 4y plus 6 over 5. And then we want to solve for y equals. Well, here's our y equals term up here in the numerator, so the first thing we're going to do is multiply both sides by 5. So we get 5x equals 4y plus 6. Then we're going to subtract 6 from both sides, so we get 5x minus 6 equals 4y. Then to get y by itself, we're going to divide both sides by 4, so we get y equals 5x minus 6 divided by 4. Last step says replace the y with the f inverse, so our inverse function is going to be 5x minus 6 divided by 4. Okay, again, the domain of f, yes, there is a fraction, but there's no variable in the denominator, which means there's no way that fraction is going to be undefined, so the domain would be all real numbers. The range of f, same thing, is going to be all real numbers. So then we can say, well, then the domain of f inverse is all real numbers, and the range of f inverse is going to be all real numbers. Alright, and one more. Let f of x equal the square root of x plus 5. Find the f inverse, or the inverse function. Well, we start out, replace f of x with y, so we get y equals x plus 5. Switch x and y, so we're going to say that means x equals the square root of y plus 5. Well, we're trying to get the y out from under the square root, so what we're going to do is square both sides. So we get x squared equals y plus 5. And then to get y by itself, we're going to subtract 5 from both sides. So y is equal to x squared minus 5. And then our last step is replace the y with f inverse, so we get f inverse is equal to x squared minus 5. So then we come down here, we talk about the domain of f. Well, f has a square root, and remember, you cannot have a negative number under the square root, so the domain for f would be all x values that make x plus 5 greater than or equal to 0, which means x is greater than or equal to negative 5. The range of f, if you take the square root of a number, you cannot get a negative number. We could get square root of 0 is 0. The range of f is going to be all real numbers greater than or equal to 0. Now when we talk about the inverse function, if f inverse is x squared minus 5, the domain would be all real numbers, because we could plug whatever we wanted in for x, and the range, well, x squared is going to be a parabola opening upward. The minus 5 means that has shifted it down 5. 1, 2, 3, 4, 5. So the range is going to be all real numbers greater than negative 5. Notice that the domain of f inverse and the range of f are not the same. So sometimes what we have to do is we need to go back and restrict the domain so that they are the same. So we're going to say that the domain of this f inverse, x squared minus 5, is not all real numbers. It's all real numbers greater than or equal to 0, because if you'll think about it, the graph of x squared minus 5 is not a one-to-one function. It would be for x is greater than or equal to 0, because then we're not even going to talk about this side. We would just have this side of the graph, which is 1-to-1. So we'll just go in and limit our restriction so that we get the domain of the inverse to equal to the range of f. Okay, let's do an example with a table. Use the table to evaluate f inverse of 1. Well, f of 1 would mean find the y value when x is 1. F inverse of 1 means find the x value that gave us a function value of 1. So if f of x is 1, then f inverse means the x value that gave us 1 was 6. So f inverse would be 6. Objective 7. The graph of f inverse of x. If f and f inverse are inverse functions, and f of a is equal to b for real numbers a and b, then f inverse of b is equal to a. What that means is, if the point AB is on the graph of f, then the point BA is on the graph of f inverse. So here's our picture that shows here's the ordered pair AB for f, and then the ordered pair BA is on there for f inverse. And if a function is 1 to 1, the graph of its inverse function is a reflection of the graph of f across the line y equals x, which means if you folded your paper along this line y equals x, then the graphs would overlap on both sides. Notice this one goes up here and this one goes down here. Okay, let's do an example of this. Let f of x equal 3x plus 1. And we want to graph the function y equals f of x, y equals f inverse of x, and y equals x on the same set of axes. So f of x is equal to 3x plus 1. If we were going to graph this, I'm just going to use the fact that y equals mx plus b, so this line would have a y-intercept of 1. And the slope is 3, which means 3 over 1, which means we're going to go up 3 and over 1. Or we could have gone down 3 and back 1. So this is what this graph right here looks like. Now, technically, if we looked at the graph of y equals x, that means we go over 1, up 1, over 2, up 2, over 3, up 3. So that y equals x line is that 45-degree angle going right through here. So what should happen is, when we know our points, if this is the ordered pair over 0 up 1, then the inverse function would be over 1 up 0. And if this is the ordered pair over 1 up 4, then the f inverse would be over 4 up 1. So basically these points, this point and this point, are the same distance from the y equals x line. This point and this point are the same distance from that y equals x line. Now this point right here was back 1 down 2. So the f inverse would be back 2 down 1. So we get our graph that's going this way right here. We could also just find f inverse, which means we're going to take y equals 3x plus 1, switch the x and y, so we get x equals 3y plus 1, subtract 1, so x minus 1 equals 3y, divide by 3, and we get x over 3 minus 1 over 3, which means it has a y-intercept of negative 1/3, and then the slope, that's like saying 1/3 x minus 1/3 equals y, which means we're going to go rise 1, run 3. So from 1/3 we are going to rise 1, run 3, and we're back over here. So lots of ways we could do this. I think the easiest way is to do your chart, find some points, and then just interchange the x and y, and that would give you the graph for the f inverse. So in summary, if f is 1 to 1, then the f inverse exists. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. And thirdly, if the point AB is on the graph of F, then the point BA is on the graph of F inverse, so that the graphs of F and F inverse are reflections of each other across the line y equals x. You are now ready to complete this section of homework in my math lab.